alguma coisa?
Eu entendo razoavelmente.
Entende razoavelmente?
Posso pedir um tempo em português?
Pode, claro.
Ah, ok.
Tá. You are? Okay. Well, yeah, maybe other people will come that for which for who English would you prefer if I spoke Portuguese?
I would say yes, but
Okay. Well, I prepared the class in English today. Let's see who else comes, and then depending on that, I can switch to Portuguese next time. Okay. So let's start with the introduction. The references for the course are, these three that I'm listing. There are many other textbooks and good references for this material. So the course is called Topology of Manifolds, but it's also known as Algebraic Topology. So yeah, I mean, the emphasis on the course is going to be less on manifolds than maybe what's written on the IMPA site, because other courses take a lot of the emphasis on manifolds. So I'm going to emphasize more of the algebraic aspects of this. So we're going to be mostly talking about topological spaces in general. There will be some particular kind of topological spaces that we'll talk about a lot, such as CW complexes, simplicial complexes. We will talk about manifolds sometimes, but not always. So the goal of this course is to understand some invariants of topological spaces, so that come from algebra. Okay, so the first reference is probably the most important one, is a relatively new book by Hatcher. I guess it's not so new anymore, but I have the book here. And the great thing about this book is that it's available online for free on his website. So you don't have to go to a Russian source. So this is freely free online. So you can just download that. And if you want to buy it, it's not very expensive. And then BREDON is a very nice book. It's a little bit more, there are more manifolds in it than in Hatcher. I'd say it's a little bit more geometric. So it's a good reference. Sometimes I'm going to use this book. I'm going to mostly follow Hatcher, but I'm going to go into this a little bit. And then a third one, which is I'm not going to come very close to, but it's very related. There are many important things, is Bott and 2. So Bott and 2 starts with the Rum cohomology, which is something I think, I'm not sure about you, but I'm sure you've seen the Rum cohomology in the first year of master's. It's taught in the Analysis on Manifolds class, and it's kind of the first idea. But then this book goes in a slightly different direction into other things in algebraic topology, including spectral sequences and check cohomology, things that I'm not sure I'm going to be really able to cover in this course. So let's see how the course goes and how fast we can move through the material, and how interested you are in the different topics. But the main goal of the course is to talk about homology and cohomology. So in different ways that we can talk about them, but these are the most basic invariants of algebraic topology, homology and cohomology. Okay, so about the grading, we'll have problem sets, which won't be every week, but maybe every 2 weeks. Will be 50% of the grade, and then we'll have the final exam, which will be 50% of the grades. Okay, so with that said, let's start with the introduction. So I guess the main question that guides this whole subject is how to tell topological spaces apart. So how to tell topological spaces apart. Okay. Well, if I give you two topological spaces, how do you know if they're the same or if they're different? So what does it mean to be the same? So the most basic definition is the idea of being homeomorphic. So let me just write this down. I think you're all familiar with this, but let's start with a simple definition. So if we take X and Y topological spaces, they are called homeomorphic. if there exist two functions, f from x to y and g from y to x, such that their composition is the identity in their respective spaces. So f composed with g is the identity on y, and g composed with f is the identity on x. And I should say once and for all that every time I write a function on this course, unless otherwise stated, it's going to be continuous. So all the sets you see, almost all of them will be topological spaces, and all the functions will be continuous. So I'm always going to assume that. So I don't have to say continuous all the time. Okay, so if I have a function from x to y and an inverse from y to x, then I say that the two topological spaces are homeomorphic. So that's kind of the most basic idea of being the same. Okay? So for example, if I think of a sphere as a subset of R3 like that, and I think of another set, I don't know, something like that, these places are homeomorphic. So a notation that I'm going to try to be consistent with is that when something is homeomorphic, I'm going to use this congruent sign. I mean, these signs depend a little bit on who you talk to, the particular book, but for me, at least for now, this is going to mean homeomorphic. Okay? And then, of course, it's not very hard to see, or to understand, at least from the picture, that if you draw a torus like that, and you draw a surface with two holes, that these guys are not homeomorphic. Okay, so one of the goals is to say, well, how can we tell these spaces apart? And in fact, this is not homeomorphic to this either. So why is this homeomorphic to this, and why is this not homeomorphic to this? Well, if you write down what this is in, I don't know, with a function or something, you can actually find a homeomorphism explicitly if you want. But there are maybe smarter ways to do that. But I think initially a harder question is how do you tell that two things are not homeomorphic? Right? You have to show that no matter what you write, it cannot be a homeomorphism. So that's not a super easy thing to do. You have to show that there exists no function that is a homeomorphism. And that's where the algebraic topology comes in hand. So we'll learn in this course some tools to be able to set these spaces apart. So basically, you take a topological space, you strip it down of a lot of structure, and you end up with some simple algebraic object. And then you show that this algebraic object is preserved under homeomorphisms. So if the algebraic object is different, then the spaces can't be homeomorphic. So in this case, for example, if you have surfaces, we can think of a very simple algebraic structure, which is just a number, the number of holes. I mean, we can make that more proper, as you see in the next couple of weeks. And then you see, well, this guy has one hole, this guy has 0 holes, and this guy has 2 holes. So they can't be homeomorphic. Okay, so that's the most primitive thing that one can talk about. Now, actually, in topology, we want to identify things that are maybe not homeomorphic, but that are similar in some way. So for example, now if you look at a band like this, also called an annulus, and a circle. These spaces, they're not quite homeomorphic, but they're very similar in some way. Right? The property that's interesting about them is that you can think about the circle as being a subset of this guy. And somehow this whole annulus, this whole band, it shrinks down to a circle in a very nice continuous way. So we would like to say that in some way they are also equivalent topologically. So what is this? What concept is this? So this is called a deformation retraction. So let me do this definition, which is, so let y be a subset of x. We say that a function from x to y is a deformation retraction if. So if a few properties are satisfied, first it has to fix y. So R restricted to y is the identity of y. And then it has to somehow, you have to have a homotopy from R to the identity map. So what is that? So that there exists some function f that goes from x times 0, 1 to x such that, well, f, so you want f of dot, you want this function to interpolate between sorry, you want this function to be to interpolate between R and the identity. So this is the identity on X. So it goes between this R and the identity. And it has the property that for every t, if you are on Y, you're always the identity on Y. Okay, so that means I can take the whole band and I can deform it to this R. So I start with the identity function on the band, for example, or on any x, and I can actually deform it continuously to this retraction R. So this is what a deformation retraction is. Okay? And of course, if there exists a deformation retraction from x to y, we say that x deformation retracts to y. So we say, in this case, we say that x deformation retracts to y. Okay, so this is a very important concept. And in this case, when a space deformation retracts to another one, they are topologically equivalent in some way. Okay? So an example of a deformation retraction is what's called a contraction. So definition, if you have a topological space, so if x deformation retracts to a point in X, we say that X is contractible. So I'm sure that you've all heard this notion before of contractibility. So a space is contractible if you can basically shrink it to a point using a homotopy like this. Okay, so that's the same as being deformation, as the point being a deformation retract of the whole space. Okay, so this is kind of topologically we would say that the space is equivalent to a point. Okay, so this is still kind of a strong notion of equivalence. So for example, if let's say that you have two spaces that both deformation retract to the same space, then you'd like to say that somehow they're equivalent. Because this deformation retraction is not an equivalence relation, unlike homeomorphism. So we need another notion that's a little bit bigger than deformation retraction. Some notion of equivalence of spaces that's weaker than homeomorphism, that encompasses deformation retraction, but that's a little bit bigger. Okay, so that's maybe one of the most important ideas in topology, which is the idea of a homotopy equivalence. So before that, let me just kind of say what it means for two maps to be homotopic. I think this is, again, maybe something you've seen in some course before, analysis or something. So if you have two maps from X to Y, you say they are homotopic if there exists basically something interpolating from one to the other. So if there exists a map F from X times 0, 1 to Y, such that F of dot 0 is f0, and f of dot 1 is f1. Okay, so that's the idea of two maps being homotopic. So now, with this notion, we can define what it means for two spaces to be homotopy equivalent. So it's probably the most important definition of today. So X, say that X and Y are topological spaces. X is homotopy equivalent to Y if there exist functions, functions f from X to Y and G from Y to X. Well, homeomorphism would mean that both compositions are equal to the identity. Homotopy equivalence is going to be that both compositions are homotopic to the identity. So, such that the composition of F and G is homotopic. Oh, I forgot to write the notation. Let me just say that if they are homotopic, then I will write that F is homotopic to G like that. So just one bar. Okay. So if the composition is homotopic to the identity in Y, and the composition of G with F is homotopic to the identity on X. Okay? And that's kind of the most important notion of equivalence in topology. So all the invariants that we'll see, almost all of the invariants we'll see in this course, will be invariants of homotopy equivalence. So you won't be able to tell apart things that are homotopy equivalent, but you will be able to tell. The hope is to be able to tell things apart that are not homotopy equivalent. Okay? Any questions about this?
What notation are you going to use to inform if two spaces are
Homotopic. I'll use the same notation as homotopic. So I'm going to write it like this. Yeah. So just the name is important to remember. We don't usually say the spaces are homotopic. You say the maps are homotopic, but the spaces are homotopy equivalent. It doesn't really make sense to say the spaces are homotopic. Sometimes, if you have two spaces that are included into a bigger space, maybe someone will say the spaces are homotopic, but what they really mean is the inclusion maps are homotopic. Okay? So I guess an example of that, of two spaces that are homotopy equivalent, are two spaces that both deformation and retract to the same thing. For example, if you can think of a solid torus. So this is with the whole interior. So this is a three-dimensional. Sorry, my drawing is not amazing. And you can think of the band. Well, sorry, in this case, this deformation retracts to this. But you can think of, well, like say that you take this, and you take the union with a sphere, and then say you take this guy, and now you take a thickened sphere. So okay, so sort of this guy deformation retracts to the circle, and this sphere shell deformation retracts to the sphere. So you see that neither one deformation retracts to the other, but they both deformation retract to the same thing. They both deformation retract to a circle glued to a sphere like this. Okay? So it's not very hard to see if you write things down that, in particular, they are homotopy equivalent. Okay? But in principle, homotopy equivalence is more general than being deformation retracted the same thing. There you can cook up examples of more complicated things. Okay? All right, so let me talk about one more example, one more kind of map, which is a retraction. So it's not a deformation retraction, but a retraction, which is something more general than a deformation retraction. So a retraction is basically plays the role of a projection in topology. So a retraction, so let's suppose Y is contained in X. A retraction is a map R from X to Y such that R restricted to Y is the identity of Y. So that's the only thing you're interested in. So if there is a map, basically if there's a continuous extension of the identity of Y to all of X. So that's called a retraction. Okay? So in general, that's of course a lot easier to obtain than a deformation retraction because you're not asking for the space to go for this map to be homotopic to the identity, but it's still actually not always possible. So one very important theorem that will prove is that if you take the ball in the sphere, so let me define the ball. If you take the n-dimensional ball, which is the set of elements in Rn, whose norm is less than or equal to 1, and you take the sphere, which is the shell, the boundary of that. So a theorem, which we'll prove using our invariance, is that there is no retraction from the ball to the sphere. This is not very obvious if you think about it, but it's true. And I mean, a retraction is not an equivalence. It's not necessarily a homotopy equivalence. So it's possible for there to be retractions without spaces being homotopy equivalent. For example, if you take a point, every space retracts to a point because you can just take the map that maps everything to a point. Right? So, of course, that if that was homotopy equivalent, then there would be no interesting theory. So, everything retracts to a point. But you see that, that's one of the reasons why this theorem is quite interesting. Like everything retracts to a point, but you cannot retract the ball to its boundary, to the sphere. Okay? So we'll see later in this course, maybe in the next few weeks, a proof of this. So you can prove this using homology, for example. Okay? So if you believe this, then we can prove a very nice theorem, which is called the Brouwer fixed point theorem. So a corollary of this is what's called the Brouwer fixed point theorem. So it says the following. So it says that every continuous function from the ball to itself has a fixed point. Okay? So how do we prove that? Well, suppose that you have a function that doesn't have a fixed point. So suppose you have a function such that f of x is different from x for every x in the ball. Okay? So then we can actually cook up another function. So I'll draw a picture. I can write down the formula. It's not, the picture is more enlightening than the formula. So take a point x, take its image f of x, And then we can look at the line that goes through f of x and x. That's oriented from f of x to x. And you can see where it hits the boundary. So because f of x is always different from x, this is always going to be well defined. And there's going to be a unique point where it hits. So this point I'm going to call g of x. So let g of x be this function. Okay. I mean, I wrote down the formula if you want to know. It's extremely ugly, but it's not very hard to find out. It's just a easy vector calculus, or not even calculus, vector linear algebra exercise. So g of x is, get ready, f of x plus some number times x minus f of x. And the number is extremely ugly. It's minus, well, it's not that bad. The inner product of x minus f of x with f of x plus the square root of x minus f of x squared plus this norm times 1 minus norm of x squared. So this square root divided by x minus norm of f of x squared. Okay, it's not so bad. So that's g of x. So maybe from the formula it's hard to see that it's always on the boundary, but you can actually prove that. The norm of g of x is 1. And g of x fixes the points on the boundary. So g of x equals x for every x in Sn minus 1. I mean, it's clear from the picture that I drew, and you can check that. So G is a retraction from the ball to the boundary of the ball. And that's a contradiction because of this theorem that we didn't prove. Okay? So this is a contradiction, and that's the end. So of course that there's a lot of content in that theorem. Okay, so this is just to warm up, so you guys see a very interesting, the kinds of arguments that will come up in algebraic topology. Okay, so in general, the goal for us in this class will be to find homotopy invariance. So the goal is to find invariance of homotopy equivalence. Equivalences. So the first idea, the most basic invariant that one can think for a connected, for a topological space is the number of path-connected components. So the idea 0 is like looking at the number of the path-connected components. I mean, you could maybe think about just connected components and go into like pathological examples, but because we're doing homotopy, everything that is interesting to us is about homotopy equivalence. Then it's a lot more. It's a lot easier to just think about path-connected components. And in practice, we won't really be dealing with very pathological spaces, so that's not going to make a big difference for almost all the examples we'll see. Okay, so what is this, or how can we think of a path-connected component? Well, you can think about all the maps from a point to the space, and you can mod out by homotopies. So this is the following thing. So consider the set of all functions from a point to the space, well, that's the same thing as just thinking about points in the space. And you quotient by homotopies. Okay. So this quotient space is the same thing as the set of path-connected components. Okay? So, we're getting to a little bit of an abstraction thing here, but I think it's the right place to start. So this is also denoted like this. This is the set of the set of homotopy classes of maps from the point to X. So this is the notation that I'll use sometimes. So this means the homotopy classes of maps from this space to this space. Okay? So of course this it's not hard to see. So an exercise is that this is preserved. Well, actually, this is also called pi 0. Okay. So an exercise is to see that pi 0 of x is preserved under homotopy equivalence. And to be more precise, I shouldn't really say number of path-connected components. I should say set of path-connected components, because it could be a non-finite number. It could be an extremely complicated set. So I should say the set of the path-connected components. So the set of path-connected components is defined like this, and it's what's called pi 0. Okay, so that's kind of the most primitive homotopy invariant. Okay, so well, this is kind of course, we know this doesn't get us very far. We can think of a million different kinds of connected spaces. So they only have one connected component. So the second idea, which I'll call idea 1, is what's called the fundamental group. So I think, I'm not sure if you all know very much about the fundamental group. Has anyone taken the fundamental group class? Oh, you've taken it. OK. So, and I'm sure you've learned about the fundamental group. Yeah.
Yeah.
So let me just quickly say a few words about it. So the idea of the fundamental group is that instead of taking homotopy classes of a point to an x, maybe you would like to take homotopy classes of loops. So you want to, for example, distinguish surfaces. You want to say, well, how do you know that the surface has a hole? Well, because there's a circle that can't be contracted to a point. Okay, so sort of, we would like to say something like this. We'd like to take the homotopy classes of maps from S1 to the space. This is called the free loop space. It's not the fundamental group. And the problem is that, well, this is a nice set, but it's not very easy to think about how to compose two of these things. So it's kind of a funny set. So this is called the loop space. So instead of doing that, what one does is so if you want to actually really compose things and get a nicer algebraic object, which is the fundamental group, then you'd like to compose things. So to be able to do that, we have to fix a base point. So we fix a point in S1, and we fix a base point in X. So now we were going to take homotopy classes of maps, and I'm going to write it like this: from the pair S1P to the pair XX0. That just means that I'm looking at maps from S1. So this means I want maps from S1 to X, which take P to X0, and I want to quotient out by homotopies. But of course, I want the homotopy to always, for every point, to be always take P to X0. So homotopies. Okay, so I want to quotient this out by homotopies. And this space is a very famous fundamental group. So this is known as pi1 of x with respect to x0. Okay. How do we compose elements in this? Well, we can reinterpret this as maps from the interval relative to the boundary of the interval to x0. So now I'm looking at homotopy classes of maps from the interval to x that take both ends of the interval to x0. So I is just, say, the interval 0, 1. And now how do I compose? Well, if I have two maps, f and g, from I to x, I can write a composition which takes t to f of 2t if t is 0.5, and then g of 2t minus 1 if t in half 1. So the first half of the interval I do f, and the second half I do g. And then you actually can show that this, the homotopic, the equivalence class of this doesn't depend on which representative you pick for the equivalence class of f and the equivalence class of g. So, this is maybe the first class of fundamental group. You prove that. So exercise, you prove that the homotopy class of this only depends on the homotopy class of f and the homotopy class of g. So you can actually, so this guy actually defines the product of the homotopy class of the equivalence class of f and the equivalence class of g. Okay, so this defines an operation on this set, which in principle is just a kind of a crazy set. It's just a set of equivalence classes. And then finally, to show that it's a group, we have to show that there is an inverse and there is an identity. So it's not very hard to see the identity. It's just the constant map is the equivalence class of the constant map. So you let 1 be the equivalence class of the constant map, and you let minus f be, well, you define minus f to be the function that takes t to f of 1 minus t. So you go, you do this, you take the same path but the other way, and then you show that it doesn't depend, the equivalence class of this doesn't depend on which representative you pick. So you can define minus the equivalence class of f as the equivalence class of minus f. And then you have to show that f composed with minus f is the identity, and vice versa. And that's it. So that will show that this is a group. Okay. Maybe minus is not the best notation because, well, it's not necessarily a commutative group. So I'm sure you've seen lots of examples. So let me just remind you. If, for example, if you take a circle, S1, the fundamental group of S1 with respect to any point is isomorphic to Z. So it's a free abelian group with one generator. So it just depends on how many times you're going around S1. So this is a nice little thing to prove. But again, since you've seen this before and it's not part of this class, I won't prove that. But if you want to review fundamental group, you can look at Hatcher. The first chapter on Hatcher covers the fundamental group and covering spaces. So you can look at that. It's a nice source. Yeah, I also should say that a remark is if X is path connected, then the fundamental group of X with respect to some X0 is isomorphic as a group to the fundamental group of X with respect to some other y0. In fact, even if it's not path connected, this will be true if x0 and y0 are in the same path connected component. Okay, so the fundamental group only depends on the path connected component. Although this isomorphism here is not canonical in general. So there is an isomorphism. So the groups are the same, but this isomorphism could depend on the path from x0 to y0. So if you have say you have a set like this, and here is x0, and here is y0. The way you show that this is an isomorphism is you pick a path from x0 to y0. And now if you have a loop here, you just compose with this path at the beginning and at the end. And this is going to determine one isomorphism. So if you take another path that's not homotopic to the original path, then you have a different isomorphism of groups. So if you want to play around and try to understand what's going on, you could, for example, look at this example, and you see that you're going to have a conjugation in general. I mean, in this case, it's connected. So, I mean, in this case, it's a billion. So conjugation is it's nothing. But if it's not a billion, then a conjugation actually does something. So the second example of space, which is already quite interesting, is what's called the wedge sum. So the wedge sum is what the picture I think I just erased. So you take two topological spaces, you take 2 points in them, and then you glue the points. So you identify 2 points. So you take the quotient topology. So this is you doing this. So what's the fundamental group of this? Yeah, so the fundamental group of this is the free group generated by two guys. So, say that you have one generator here that you call A, one generator here that you call B. So now if you want a closed loop, you can go around A as many times as you want, then you can go around B, then you can go around A, then you can go around B backwards. So, this is going to be the free group generated by A and B. So what does that mean? Let me say this again. So this is a set of words in A and B. So this is a set of words in A and B. And say, yeah, so what does it mean? That means that a word is going to be something like you write A a number of times, then you write B a number of times, then you write A, then you write B, etc. And you can write inverses as well. And then under the equivalence, the obvious equivalence, which is that if you have A and A inverse next to each other, you can cancel them out and put an identity. Okay, so under the obvious equivalence. So I won't get too much into this, but there is if you really want to understand what the free product is, you have to dig a little deeper into the algebra. But it's not very hard. It's just a little hard to write down. So this is also called the free product of Z and Z. So it's kind of like the largest non-abelian group with two generators. Okay. So what about the torus? What's the fundamental group of the torus? Do you remember from the class? Yeah, so this is actually the free abelian group in two generators. Well, I won't explain. Well, I can roughly explain how you get this. So you can think of the torus as something like this. So here's A, here's B. So, of course, you have this loop A and this loop B, which are not contractible. But if you take the loop A, B, A inverse, B inverse, you have a contractible loop. So the idea is that this guy is going to be this free group generated by A and B, but modded out by a relation, which is given by A, B, A inverse, B inverse, which is exactly what breaks the non-commutativity. Okay. And you see that this gets a little complicated, but there's a very nice theorem called the Van Campen Theorem, which gives a very nice recipe to compute fundamental groups of spaces by breaking them up. It's kind of complicated because groups are complicated. And in fact, there's a theorem which I'm not sure if you've seen, but I can explain in a few words, which is that every group is the fundamental group of some topological space. So every group G is pi 1 of x for some x connected space. And the way that you can prove this, let me just say it in words, is, well, every group can be given by a set of generators and a set of relations. So every group can be written as a free group on its generators, quotiented out by some relations. So what you do is you take the generators, and you take the wedge sum of S1s for each generator, where this could be even like uncountable. The set of generators could be extremely large. But that's fine. You can take the wedge sum over an uncountable set of S1s. And then you have to add 1 cells according to each relation. So for example, if you wanted to make the group commutative, you wanted to do A, B, A minus 1, B minus 1. If that's your relation, then you add a 2 cell that glues like that, A, B, A inverse, and B inverse. But if the relation was more complicated, you can add a 2 cell whose boundary gives that relation. So when we talk about CW complexes, maybe this is going to be easier to understand. But this is not a very hard thing to prove. But it's very powerful because it basically tells you that if you really want to understand fundamental groups, you have to understand groups. And groups are very hard. Group theory is a very difficult theory. But nonetheless, this is actually a very simple thing to define, which is why people talk about it. It's a simple thing to define. It's not so simple to compute, but it's simple enough to define. OK, so with that said, well, this means it's very complicated, but it's not enough to understand things. You can very easily cook up an example where the fundamental group doesn't give you everything. For example, just look at the 2-sphere. What's the fundamental group of the 2-sphere? It's trivial. And of course, the 2-sphere is not contractible. So you would like to be able to tell apart the 2-sphere from a point. So what can you do? Well, you can actually, one idea is to generalize the fundamental group to higher homotopy groups. So let's talk about that quickly. So you can think about higher homotopy groups. So what's that? So instead of thinking about equivalence classes of homotopy classes of maps from S1 to X, you can just take a higher sphere. Right? You can take maps of Sn to X. And again, if we want to have a group, then you have to fix a base point. So you take Sn with a base point, and you map it to X with a base point. So this, the equivalence classes of maps from that, like homotopy classes of this is what's called pi n of x, x0. OK? And then we have to define a group operation. So let me do that. So this is, again, you can think of this as a map from the cube to the space X that takes the whole boundary of the cube to x0. OK, so this is a map from I to the n relative to its boundary to x relative to x0. And how do you compose? Well, choose one component of the cube and compose on that component. So it doesn't really matter which one you pick. But let's say, so f and g are mapped from I to the n to x, and you can define the composition to be something like this. So T1 through Tn, it goes to f of t1, tn minus 1 to tn, and g of t1, tn minus 1 to tn minus 1. So if tn is between 0 and half, and if tn is between half and 1. Yeah?
Is it actually the sphere or the torus?
The sphere.
The sphere.
Yeah, homotopy maps of the sphere. Yeah, so if you think about a cube,
There's a how to think of that.
yeah, think about the square. So if you take the square and you identify the whole boundary to a point, what you obtain is actually a sphere.
Oh, okay.
Okay? And this is in any dimension. If you take a cube and you collapse the whole boundary of the cube to a point, you have a sphere. Okay? Of the same dimension. So what the picture that you could draw here is, think about f as a map that's defined on a square, and g as a map that's defined on a square. So the composition of the two, according to this rule, is basically you take your square and you split it like this. And this glues well because this is x0 here. So on this colored part, the map goes to x0. Okay, is this picture clear? And of course, homotopy classes. Okay. Now there is a very nice little theorem that I'll prove for homotopy groups, which you can prove by picture, basically, which is that, so the theorem is that pi n is a billion for n greater than 1. I mean, I didn't say what the inverse was and what the identity was, but it's kind of clear that the identity is just, it's the same proof as the fundamental group. The identity is the constant map, and the inverse is just flipping the last coordinate. And of course, you can choose any coordinate. It doesn't have to be the last. But the theorem, maybe I should call it proposition because it's too easy to be called a theorem, but it's still kind of a very surprising result, is that pi n is a billion. So how do you prove that? Well, we have to prove that f composed with g is homotopic to g composed with f. So proof by picture. So what's f composed with g? That's the homotopy class of this guy. Okay. So now what you do is you say, well, this is homotopic to the following thing. I can make f in a smaller cube. I can make g in a smaller cube. And I can set, so this is this color here. Maybe you can't see. Let me put pink. The pink is what's constant equals to x0. So I know that over here I have to be constant equal to x0. So what I do is I shrink both of them to little cubes where everything here is x0. So now I flip them. No. And then finally, I go to the standard thing where I have g and f. And there you go. That's the proof. Yeah.
Does this fact imply that higher for a connected space, the higher homotopy groups do not depend on a base point?
That's also, it's the same proof as before.
Like it's fundamental group, but it's always a billion, so it doesn't depend actually on.
No, you don't need to use that it's a billion. You can do the same argument with the path. Because you can collapse, like,
No, for a fundamental group, we have automorphism.
Yes.
Like in an automorphism, that could be non-trivial.
Yes.
But if the fundamental group is abelian, then they're all canonically identified.
Yes.
But here, for higher homotopy groups, they are always canonical.
Oh yeah, that's right. Yeah, because it's abelian. Yeah, because it would differ by a conjugation.
So we can.
Yeah, so you can remove the x0. Like if it's connected, you can remove the x0. Even there's a canonical group, a canonical presentation of the group. Yeah. Yeah. It's more than they are also isomorphic. They're all canonically isomorphic. Yeah. Okay. So that's the proof that it's abelian. So maybe at this point you're like, oh great. So let's just use higher homotopy groups. They're so nice. They're abelian groups. But I don't know if you're aware of this, but it turns out that higher homotopy groups are very hard to compute. In particular, even for the sphere, it's not known, for some spheres, it's not known what all its homotopy groups are. So what is known, I can tell you that the easy part is the following. So we can prove that pi n of sk, so this is 0 for n less than k, and this is z for n equal to k. So assuming k is bigger than 0, like I don't want to talk about S0. But for n greater than k, this becomes a very, very hard problem. And it's unknown for a lot of examples. Yeah. Another thing that's interesting is that for k sufficiently large, you have that pi n of sk is isomorphic to pi n plus 1 of sk plus 1. So these are called the stable homotopy groups of spheres. So these are easier to compute for k large enough. But knowing all of the homotopy groups is still an open question. So even for spheres, so we can only imagine for more complicated spaces that this would be a very, very hard question. But it's an area of active research. People who study algebraic topology talk about homotopy groups quite a bit. And there are many interesting theorems about homotopy groups, which are beyond the scope of this course. So part of the problem with homotopy groups is you see that even for something simple like the 2-sphere or the 3-sphere, you have non-zero higher homotopy groups. So somehow the homotopy groups don't care that the sphere only has a 2-cell. It still is giving you non-zero things in very high dimensions. So that's one of the reasons why we're going to leave homotopy groups and we're going to go to homology. Because homology is a much simpler kind of invariant. It's an invariant that will vanish usually for high enough dimension. Okay. So actually it's 11:05. Let's take a quick break and then we'll come back. Maybe just less than 5 minutes just to go to the bathroom. And, yeah. Qual? Isso daqui? Olha, você quer saber se existe um espaço cujo grupo de homotopia maior é igual ao grupo. Então, o resultado que eu sei é o seguinte: dado um grupo abeliano, existe um espaço, dado um grupo abeliano e um número maior do que 1, existe um espaço que tem aquele grupo como Pn e todos os outros grupos de homotopia 0. Okay, Então, esse espaço existe. Agora, se você prescrever todos os grupos de homotopia, eu acho que você não consegue achar um espaço que tem todos esses grupos de homotopia. Isso seria muito mais difícil. Eu teria que pensar, mas eu acho que se você quiser um grupo de homotopia específico em se você quiser que um determinado Pn seja igual a G para um determinado G, você consegue, mas todos os outros vão ser 0. Tá. Bom, eu vou no banheiro. But it's easier to compute and we'll be able to really put our hands in it. There are lots of very concrete results. Okay, so let's begin with, let's remember the Euler characteristic. I think it's something you've all seen before. But the idea of homology is to try to generalize the Euler characteristic, or to try to get more information in the Euler characteristic. So I think you've all seen this. So for example, if you take a polyhedron, I think you've all seen that at some point, that if you compute the number of vertices minus the number of edges plus the number of faces, you always get 2. So even for a very complicated, I don't know. Let me not draw the same thing. Oh no, it's already different. Even for some very complicated thing, you always have this number. Okay? But if you have, if you take, say, a torus, you can think about it in the same way. You can split the torus into cells. So let's think about it like this. So I have one vertex. The vertex is the same. I have 2 edges, and I have 1 face. So for the torus, if I do v minus e plus f, I get 0. And you can see that if you split it up in different ways, in different faces and edges, you always get that this difference is always going to be the same. And it turns out that for any topological space that is triangulated, that can be triangulated, or for anything that's more general called a W complex, which we'll talk about later, this vertices minus edges plus faces, and then if you keep doing it for all dimensions, that number is always going to be constant. Okay, so this is a deep fact, and we will prove that. But this is what homology tries to generalize. So this is just a number, right? For space, these guys are all topologically S2s. This, is a T2. So this is a number that's associated to S2, number 2. This number 0 is associated to T2. For every surface, you can do the same thing for every closed-oriented surface, and you get 2 minus 2g, where g is the number of holes. So let me say that. So if you take a surface with g holes, and you split it up like that into faces, edges, and vertices, when you do vertices minus edges plus faces, this will be 2 minus 2g. So we'll prove that. But it's something that you should know. And the idea of homology is to try to get more information than just a number. So for surfaces, these numbers are enough to classify the surfaces if they're oriented. But we'll see that if they're non-oriented, it's not enough already. You could have 2 surfaces with the same genus if they're non-oriented. And even more, if you have a higher dimensional manifold or another complicated space, these numbers are definitely not enough to classify the space. So that's why we're going to look into something a little bit more complicated, a little bit more subtle about how to deal with the vertices and edges. So let's talk about what a simplex is. So a simplex is the generalization of a triangle. So a simplex, so the standard simplex, I'm going to call it delta n. So it's something that is homeomorphic to x0, xn in Rn plus 1, such that the sum of all these guys is equal to 1. Okay, so the 0 simplex is just a point. Well, let me write equal. The 0 simplex is a point. The 1 simplex is an interval. this interval, the 2 simplex is a triangle, the 3 simplex, now I don't quite have enough dimensions to write it embedded, so I'm just going to write your tetrahedron, and so on. So in general, the n simplex is homeomorphic to the convex hull of n plus 1 points in general position. So this in general position implies that you have to be at least in Rn. So so in general position just means that you don't have 3 that are on the same line or on the same face. If you remove any point, then you have a smaller set, a smaller convex hull. So this is the standard simplex. A simplex in general would be anything that's homeomorphic to the standard simplex. Okay? So if you have a simplex, you can think of a face of it. So I'm going to write it like this. So my simplex is going to be the convex hull of x0 to xn. I'm going to use this notation. So what's a face? So a face of this guy is some other simplex where these vertices are contained in these vertices. So where the set of y0 through ym is contained in the set of x0 through xn. So a face is just the convex hull of a subset of the original set of vertices. Okay, so let's say, well, I think a face could be the whole thing. So it could be equal. Okay? So with this definition, now we can think about what a simplicial complex is. So a simplicial complex is a set of simplices such that the first property is that every face of if sigma is in S, then every face of sigma also belongs to S. Okay, so if you have a simplex, then all its faces are also in it, and if you take 2 simplices, then the intersection is a face of both sigma 1 and sigma 2. Okay? And then finally, you can define the underlying topological space that the simplicial complex defines. So there's the underlying topological space which is the union of all the simplices. So this is the union of all the simplices with the induced topology. Okay. So when I say the union, I don't mean the disjoint union. I mean, if something is contained in the other, then I take the bigger one. Okay, so with the induced topology. So for example, let's give some examples of simplicial complexes. So you can think about I don't know. So here's an example. This is where I think of all these triangles and then all these guys. Okay. Of course, a graph will be a simplicial complex if it doesn't have any if all the edges connect different vertices. Okay. But in this, of course, simplicial complexes are much more general. So in this case, I want to think about all these triangles as being faces. You could, for example, you could think of a simplicial complex that has this guy and not this face. You could maybe have something like this. So you could have a simplicial complex that's kind of funny. But of course, traditionally, simplicial complexes are ways to understand a manifold or are a decently nice space. So if you have a space, topological space, that is the underlying topological space of a simplicial complex, you say the space is triangulated. Okay, so and that's actually how people did topology originally. They took a space and then they triangulated it and they understood everything in terms of simplices, which is why I'm starting with this. Okay, any questions about this? Okay, so one thing that I want to emphasize is that if you have a simplex, then you can think of an orientation of a simplex, which is basically just a way to an equivalence relation of simplices where you keep track of the order of up to even permutations. So I'm going to identify, if I have the simplex x0 to xn, I'm going to identify it with another permutation of this guy. So as long as, so sigma is a terrible letter for this, eta. So eta will be a permutation, an even permutation of 0 and n. So this is the first thing that we do, which is, well, I want to think of the simplex as like a set, not so much an ordering, but I want to keep track of signs. Okay, so from now on, I'm going to think of a simplex as I'm going to write it like this. I'm going to still write it like this, but with the understanding that if I apply an even permutation to the vertices, I'll get the same thing. And if I apply an odd permutation, then I get a minus sign. Okay, and the reason for that is I'm going to take the free abelian group on the simplices. Okay, so given a simplicial complex, S, I can first write it like this. So I can write S, all the simplices, as a union of Sk, where K is the dimension of the simplex. So where Sk is the set of all the simplices which are homeomorphic. To delta K. So I can just say that this, for example, over here, I have the 0 simplices, which are the vertices. I have the 1 simplices, which are the line, the edges, and I have the 2 simplices, which are the triangles. So I can split my simplicial complex like this. And then now I'm going to consider an abelian group, or for each k, I'm going to let Ck be the free abelian group generated by all simplices sigma in Sk. And with the understanding that I have I can put minus signs, and it's the same as reordering the vertices with an odd permutation. Okay, so the simplex now, the ordering is not well defined, but the sign of the ordering is well defined. Okay. Well, I choose one to begin with, and that's like the plus guy. Any questions about this? And now I can define a boundary operator.
The formally, this free abelian group is generated by, not by simplices, but simplices with orientations.
Yeah, so I'm thinking of a simplex here as, well, there are two ways to think about this. Well, when you fix the simplicial complex, you fix the simplices.
Yeah.
So how do you think of a simplex? You think of, if you think about a homeomorphism to the standard simplex, then you already have an orientation given, which is the orientation given from the standard simplex. What I'm trying to say is that soon, that I actually want to identify, to think about other simplices that I want to think about all the different possible ordering of the vertices, and I want to identify the ones that differ by an even permutation, and I want to put a minus sign with the ones that are odd permutations. And the reason for that is because I want to say that a face of my simplex is just what I obtain by removing some vertices. So it's kind of a subtle thing. Like if I say, think about just a triangle as a simplicial complex. So I want to think I have 3 vertices. I have one face, one two-dimensional face, and I have 3 edges. Okay. So, but what is this edge? Say this is a simplex. But do you want it to be V1, V0, V1, or V1, V0? You know, it depends on what you mean. And when you think about a face of this, it also depends on the. Maybe it'll be clear now when I write what the boundary operator does. So, yeah, the reason is that I want to be able to talk about the boundary of it in a meaningful way. And the boundary will be when I just remove one of the vertices. But if I just remove one of the vertices and keep everything in the same order, I might not have the original order. That's kind of that's actually where the issue lies. So like say that I have this simplicial complex, and say I have V0, V1, I have V1, V2, and I have V0, V2. Okay. No, say I have V2, V0 actually. So when I look at the boundary of this face, I'd like to say that it's the sum of these 3 simplices. But it's not, I mean, why would I want, how do I know that actually I want V2, V0, not V0, V2? These 2 would be different simplices. But the simplicial complex only has one of them. So either you have V0, V2, or you have V2, V0. Okay? So what I'm trying to say is that up to a sign, I want to identify all these simplices and not have this issue of which ordering I pick. So I just have to pick an orientation at first. So I pick an ordering, but I say that any other ordering is either the same thing as the first one, or minus that. Okay. Let me continue, and then maybe this will become clear. So the point is that I want to define a differential operator. So sorry, a boundary operator that will take k-dimensional simplex to k minus 1 to a sum of k minus 1 simplices. Okay? So I'm going to call, sometimes I'm going to put a k here to indicate that it starts from k. So how do I do that? So I say that I have a simplex of dimension k. So let me write this as v0 up to vn. So what is the boundary of this guy? Well, the boundary of this guy is going to be, it's going to be the sum of the faces that have one less vertex. So I want to do something like this. The sum of v0, vi hat, vn. The hat just means I omit that. But actually, to make things be well-defined with orientation, to have a very important property that I'm about to state, I need to add a sign here. And the sign will be minus 1 to the I. And then I sum this. Sorry, this is k. I sum this from 0 to k. The point is that, when you think about the boundary, things come with an orientation. So I want, when I think about the boundary of A, I really want to think of V0, V1. I want to think of V1, V2. And I want to think of V2, V0. But if in my simplicial complex, say that instead of picking V2, V0, if I had picked V0, V2, then I don't have this edge originally. Which is why I have to say, well, this is the same as this, but with a minus sign. I mean, in this simple enough example, you could actually have just picked this guy to be, you could have just switched this edge. But in general, you can't switch all the faces to have everything with a plus sign. Okay? Which is why you have to take this identification. I mean, even if we want to think about just the points, you know, the point, say a point is always just one point like this. But because you're taking the free abelian group, you want to be able to have a minus sign like that. And when you take the boundary of an edge, you really want to say that it's kind of this guy minus this guy. Otherwise, you won't have the very important property that d squared equals 0. Okay? So you want the boundary of the boundary to be 0. Okay? So that's why you need to orient things. So orientations can be sometimes a bit of a pain, but here they're not too bad yet. Okay? So you define this thing like that. Okay? And so for example, let's say that you start, let's take again this simple triangle, and I have V0, V1, V2. Let's say my simplicial complex is the following. I have V0, V1, V2. Then I have V0, V1. I have V1, V2. And I have V0, V2. And then I also have V0, V1, V2. Okay. I promise I won't be writing things like that very much. But let's do it a couple times. So we can compute the boundary of these guys. So what's the boundary, for example, of the edge V0, V1? The boundary of this guy will be, so I remove V0. No, I remove, when I remove V0, I have a plus sign. So I have V1. And when I remove V1, I have a minus sign. So V1 minus V0. Okay. And you can do the same for all of the other ones. And I think it's interesting now to go for the boundary of V0, V1, and V2. So this guy, when I remove this guy, I get a plus sign. So I have V1, V2. Then if I remove this guy, I get a minus sign. So minus V0, V2. And if I remove this guy, I get a plus sign. So plus V0, V1. So you see why this identification is important, because I could have my simplicial complex could have been, for example, this guy. This would still satisfy the simplicial complex requirement. And it would be the same topological space. But it would be very hard to write down a formula that really understands orientations. You know, like you say, oh, I just take the faces with the -1, but how do I put signs here? That's why we have this identification where we can think of a simplex as just generated by all the vertices in any order that you want. But when you compare it to the original one, you get either a plus sign or a minus sign. Is that clear? I know this is kind of confusing, but anyway. So the point is that now a proposition is that d squared is equal to 0. Or, you know, if you really want to be proper, you want to say that dk composed with dk minus 1 is 0. So when you take the boundary of a boundary, that is 0. So how do we prove that? Well, it's a calculation. It's, look at this guy, for example. Here you can see it explicitly. So what's the boundary of this guy? It's going to be V2 minus V1 minus V2 plus V0 minus v1 minus v0. So the boundary of this guy, it's a straightforward calculation, you get 0. But we'll need to prove that in general for all dimensions. So now, I apologize, it's going to get just a little ugly, but it's still not too bad. So what's the boundary of sigma? So let's say that sigma is v0 up to vk. So this is going to be the boundary of the sum from I equals 0 to k of minus 1 to the I, v0, vi hat, vn, vk. Oh, I forgot to say something important, but maybe it's kind of obvious, which is that ck is an abelian group generated by simplices. So I define the differential, the boundary operator, on the generators of the group. And then I extend it linearly. So by definition, it commutes with the sum. Okay? So sort of by definition, this is the sum of minus 1 to the I times the boundary of this new guy. So from I equals 0 to k. Okay? So now I have to take the boundary of this. So I'm going to split it in two cases because the sign's going to be a little different. So first, I can remove some guy between v0 and vi minus 1. Or I can remove someone from here to there. So this is going to be the sum of minus 1 to the I times the sum for j going from 0 to I minus 1 of minus 1 to the j times v0, vj hat, vi hat, vk, plus the sum from j equals I plus 1 to k of minus 1. So now see that when I remove the vj, I'm doing this very slowly. What's the sign that I obtain here when I remove this guy? So according to that formula, see that I have to count which guy this is when I remove it, and that's the number that goes there. So it's going to be j minus 1. And then parentheses. Okay? So I can rewrite the sum like this. So this will be the sum where I is less than, no, where j is less than I, and both are between k and 0 of minus 1 to the I plus j of v0, vi hat, no, vj hat, vi hat, vk, and then I have plus the sum where I is less than j of minus 1 to the I plus j minus 1 of this guy, vi, vj, vk. And now you can see it's 0 because I can just switch I and j, and I have the same thing with a different sign. So this is 0. So this is maybe the most important calculation in this course. I'll do it again when we talk about singular homology, but the fact that d squared is 0 is like the crucial thing. So what does it mean? It means that, so if I take the boundary, the kth operator, say that I do dk plus 1, then I do dk, I get 0. That means that the image of dk plus 1 is contained in the kernel of dk. It's more than that, it's a subgroup. The image is a subgroup of the kernel. So I can take the quotient. I can take the kernel quotiented by the image. And that's called the homology. So you can define the kth homology of the simplicial complex to be the kernel divided by the image of D. So this is kind of the most important idea in homology. Okay? So to see how this works, let's compute a few examples. Let's start example 1. Let's start with this simplicial complex without the triangle. Just I have P1, P2, P3, sigma 1, sigma 2, sigma 3. And I have no interior face. Okay, so here, what is C1? C1, well, you have to choose an orientation of these guys, but let's just take this orientation like that. Okay, so C1 is the complex generated by the 1 simplices. So this is Z with 3 generators, sigma 1, sigma 2, sigma 3. And then C0 is Z with 3 generators, P1, P2, P3. And you can compute the boundaries. So the boundary of sigma 1 is P2 minus P1. The boundary of sigma 2 is P3 minus P2. And the boundary of sigma 3 is P1 minus P3. So what's the kernel of D restricted to C1? What's the kernel of D1? So how can you obtain 0? I want an element. Tell me one thing in the kernel. Can you tell me one thing in this abelian group whose differential is 0, whose boundary is 0?
You can just add, right?
Yeah, you can add the 3 of them. So you notice that if you take the boundary of sigma 1 plus sigma 2 plus sigma 3, you get 0. Okay? And it's not a very hard algebraic argument to see that every time you get 0, you have to be a multiple of this guy. There is no other thing. So the kernel of D1 is going to be the subgroup generated by sigma 1 plus sigma 2 plus sigma 3. Okay? And the image of D2, well, there's no C2. So this is just 0. This is the 0 subgroup. So that means the first homology will just be the kernel of D1. Okay, so this is this guy here. So this is a free abelian group in 1 generator. So this is isomorphic to just Z. Now let's look at D0. So of course that when you do D0, it starts from C0. So the boundary of any point is 0. It's the empty sum. Right? So the boundary of P1, the boundary of P2, and the boundary of P3 are all 0. Okay, so that means that the kernel of D0 is everything, is all of C0. So it's a free abelian group with 3 generators. But what's the image of D1? Well, the image of D1, so this is Z of P1, P2, and P3. The image of D1 is going to be the group generated by P2 minus P1 and P3 minus P2. And the third one is the sum of the first 2 with a minus sign or something. Yeah. So you see that when you quotient this subgroup by this subgroup, what you do is you make them all equivalent. So the zeroth homology of S is equal to, so your Z of P1, P2, P3, quotiented out by P2 minus P1 and by the ideal generated by these guys, which is the same as just taking Z of one of the guys. Okay, so you see that this is just isomorphic to Z. Okay, so we computed the simplicial homology for this very first example. So let's do another one, and now I'm going to do a little bit quicker. Stop me if you get lost. But let's do the tetrahedron, the exterior of the tetrahedron. So without the interior. So now I have P0, P1, P2, and P3. So I have faces A, B, C, and D. So let's see if I can write this quickly. A is P0, P1. Let me just copy what I wrote. P, Q, R, and S. A is PQS. B is QRS. C is RPS. And D is RQP. So I chose the orientation so that all the triangles are oriented like the sphere. So, if you think about your triangle, I oriented them like this. So this, and that. Okay? So you can compute the boundaries. So the boundary of A is PQ. Well, I'm not going to write all of this down. But the point is that, C2 is generated by A, B, C, and D. But by a very similar calculation, you can see that the kernel of D2 is going to be generated by the sum of all the faces. Okay, so, let me write this down. It's the first class. We don't need to rush. So, what's the boundary of this? It's QS minus PS plus PQ. The boundary of B is RS minus QS plus QR. The boundary of C is PS minus RS plus RP. And the boundary of D is QP plus minus RP plus RQ. Okay. So maybe it's easier to see now. So when you sum all of them, you get 0. Let's see if we believe that. So if you sum this, QS, QS, PS, PS, RS, RS, and now you see the sign, QP and PQ. They cancel. And then QR and RQ, and then RP and RP. So you see that A plus B plus C plus D is in the kernel of D1, of D2. And it's, again, not a very hard thing to check that everything in the kernel has to be a multiple of this guy. So the kernel of D2, which of course is going to be the second homology, because there's no D3, is going to be just the Z generated by this guy, by the sum of the faces. Okay, so this is isomorphic to Z. Now to compute H1, I guess H1 is the most interesting one. We have to compute the kernel of D1 divided by the image. So when you look at D1, so how do you get something in the kernel? So the C1 is going to be the sum of all the edges, the abelian group generated by the edges. So if you want something closed by a similar argument to the previous thing, what you need to do is you need to go like this. You need to go on the boundary. So you need to take this edge plus this edge plus this edge, or this edge plus this edge plus this edge, or any of the other 4 faces. And you see that when you take this sum, you get exactly what you get as the boundary of a face. Okay, so this is this clear? It's actually a very important idea. So if you want to get a closed sum of edges with signs, what you need to do is exactly go around a face. So this implies that the kernel of D1 is the same as the image of D2. That's because I have all the faces. Okay, so every time I have a closed, if I close like this, then I have a face whose boundary is exactly the same thing. So the kernel of D1 is equal to the image of D2. So that means that the H1 of S, so it's the quotient of these two. So that's the trivial group. I'm quotienting by the whole group. I get 0. Okay, and then H0, a very similar argument. It's Z generated by any of them. Okay. So this is an example, I think, that if you start thinking about it, you're really going to start to understand homology. So you see that an important thing is that you actually have all the faces. If I remove a face, then H1 will stop being 0. Well, if I just remove one face, maybe not. But if you start removing, like if you remove more than one face, then you really, like for example, if you remove the face A and the face B, then when you take this guy here, there will be no face whose boundary is this closed path. So this will translate into the algebra. Okay? So this is the first calculation of a simplicial homology, and this is how people used to do algebraic topology, like back in the 19th century. So a few more things about simplicial homology that I wanted to tell you is theorem is that the simplicial homology with all the gradings, well, let me write like this. HK of S only depends on the topology of the underlying topological space. So what does that mean? That means that if I take one topological space and I take two different simplicial complexes for the same topological space, then I get the same homology groups. And even more, if I take two topological spaces which are homotopy equivalent, then they also, and I take two simplicial decompositions, they will give me the same simplicial homology. Okay. This theorem is extremely hard to prove. And it's extremely, it's very, very complicated. You have to take, have to basically say that if I have two different simplicial decompositions, I can refine them all the way to the same one. And you show that through refining simplicial decompositions, you preserve these homologies. Okay, so this is kind of the old approach to algebraic topology. The new approach is not this, for two reasons. First, because it's actually really hard to prove this theorem. And second, it's actually very hard to find triangulations to begin with. So kind of the first thing you see is that a triangulation is actually a very hard thing to find. So for the sphere, we found this nice tetrahedron, which gives a triangulation of the sphere. But say that you want to look at a torus. How would you compute the simplicial the simplicial homology of a torus? Well, we have to find a triangulation for the torus. And it turns out that the smallest triangulation for the torus is already pretty big. It has 14 triangles, 21 edges, and 7 vertices. So that's quite a lot of, if you actually wrote down what it is, you can look up on Google or something, you can find the image. And if you want to compute this like this, it'll be, I don't know, lots of blackboards. Because you have to analyze 14 generators for C2, 21 generators for C1, and 7 generators for C0. So instead, you can do something that's slightly simpler. You can actually, just think about your good old picture of the torus. Break it up into triangles. You can just do it this way. So that means you have P, 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 and P. Here you have, say, A and B. No, A and A. And then B and B. And here you have C. Yeah, exactly. So this is the point. This is not a simplicial decomposition. Why? Because, well, this, you'd like to say this is a triangle, but the 3 vertices are the same. So this is not a simplex in the simplicial complex way. But you see, it's almost a simplex in some way. I mean, the interior is the interior of a simplex. So this is called a semi-simplicial complex, or what's called a delta complex decomposition. So let me just define this, and then we'll end the class. So definition. Let me not mess up. So a delta complex structure. So this is the notation the name that Hatcher calls it. But I think at some point in the past it was also called a semi-simplicial decomposition for a topological space X is a collection of maps So these are maps indexed by some alpha that goes from a simplex to X, where, of course, the dimension of the simplex depends on alpha. So n is a function of alpha, but I'm not going to keep writing that. Such that, well, every point in X is contained in the interior, in the image of sigma alpha restricted to the interior of delta n for a unique alpha. So every point is in the interior of a simplex. Even the vertex is in the interior of a zero simplex is a zero simplex. That's the only thing to be careful, because you are in R0, say. So the second property is that when I restrict that to the interior, this is injective. For all alpha. Okay, so in the interior, I have an injective map. On the boundary of the simplex, I could have something more complicated like this, which is not injective. The third property is that if you restrict sigma alpha to a face, that's going to be another map. So sigma alpha restricted to a face of delta n is sigma beta for some other beta. And then there's a fourth, more technical condition, which is the topology of the space is the induced topology. So I'm gonna just write it, but not really emphasize it, which is that a set is open if and only if the preimage of A inside of delta n is open. Okay, so that's just a technical condition. But anyway, this is something that's much more general than a classical triangulation. And with this delta complex structure, or semi-simplicial decomposition, you can do the same exact definition of simplicial homology. And you can compute the simplicial homology of the torus. Okay, so for in this case, let's do that. So since today we're not extremely formal yet, I'm just going to do this without defining. But I think based on the previous definition, it's not very hard to see. So in the case of the torus, I can find a delta complex structure which has, let me rewrite it. It has three edges. So I have A, B, and C. It has one vertex. And it has two faces. So I can write the three abelian groups, C0, C1, C2. So C2 is A and B. C1 is little a, little b, and little c. And C0 is just P. And now I have to compute differentials. So I oriented everything so that I won't get confused. And let's just say A and B are oriented as normally in R2. So that means the boundary of A is A plus C minus B. And the boundary of B is B minus A minus C. The boundary of A is 0. The boundary of B is 0. And the boundary of C is 0. Okay? Because it's P minus P. They're all the same. And of course, the boundary of the point is 0 because it's a 0 complex. So now I just need a little bit of algebra to finish the calculation of the homology. So what's H2? So H2, and I'm going to write the notation directly. I'm going to write it like this, delta of x. This is the notation that Hatcher uses. So I have to look at the kernel of D2. So to get something closed, I need to take A plus B. Okay, so this is going to be Z of A plus B. Well, if you see that if you take A plus B, you get 0. Maybe it's again you have to think a little harder to say that every time you get 0, you have to be a multiple of A plus B. But it's not so difficult. So this is isomorphic to Z. Now H1 is a little more interesting. So you see that you have 3 guys which are in the kernel. So the kernel is freely generated by A, B, and C. But then you have to quotient by these relations. So what do these relations say? This relation says that B is equivalent to A plus C. So that means that this is isomorphic to basically A and B. So this is something you can check. Or if you want, C is isomorphic to B minus A. Okay, so it's again an algebra exercise to see that there is an isomorphism between this quotient and the free abelian group generated by A and B. So this is a Z squared. And then finally, H0. Now it's easy because I only have one point. So this is just Z of a point, which is Z. Okay, so this is the calculation of the simplicial homology of the torus, much easier than if you actually wanted a genuine triangulation. Okay, so you can do some exercises and compute simplicial homologies of a lot of things using the semi-simplicial decomposition. But again, you have a theorem like this, that the homology depends only on the topology of the space and not the semi-simplicial decomposition. And that is still very hard. So the approach that we're going to follow, which is the more modern approach in algebraic topology, is to define a much crazier and kind of homology, which we'll see next time. It's called singular homology. But it'll be a lot easier to prove all the technical results. And we'll eventually prove that it's isomorphic to the simplicial homology. So one last comment before we finish is that, so I think eu vou trocar para português, até porque o Dimitri quer ouvir português, então a partir da próxima aula eu vou falar em português. E a aula de 2 horas eu vou explicar por quê. Porque eu vou precisar cancelar várias aulas. Então, eu vou viajar alguns momentos, então eu vou fazer aula de 2 horas e vou simplesmente cancelar algumas aulas ao meio do caminho. Tá? E aí no final a gente vai ter a carga horária normal, mas com várias aulas canceladas. Tá? E a primeira lista eu passo na quinta-feira também.